the last class we had talked about covalent bonding. We went over how it happens, and we looked at a number of examples. So it's the sharing of electrons between atoms. We looked at multiple examples where single covalent bonds are formed. They're formed between non-metals basically, and right, we looked at different atoms forming different numbers of covalent bonds, but we also looked at right double covalent bonds. So right, the examples on these pages that you see are of single covalent bonds, so just one pair of electron being shared between atoms. Carbon dioxide and oxygen are examples where double covalent bonds are formed. Right, so if I just write the diatomic oxygen is right a double bond between two oxygen atoms. And right, you even have cases of three covalent bonds. Right, a triple covalent bond, and an example of that is a diatomic nitrogen molecule. So there are three pairs of electrons being shared between the two nitrogen atoms. And of course, you don't only have these diatomic molecules or simpler ones. You've got other molecules that are bonded covalently that are larger. Although methanol is not exactly an example of a large molecule, right? But still, you can see that you've got carbon bonded to three hydrogens, a single oxygen, and then the oxygen is bonded further to another hydrogen.
Yeah.
Now, continuing with covalent bonding, we've covered the bonding part. Now we're going to talk about covalent structures and the properties of covalent compounds.
Could you repeat that again? We will discuss what?
Covalent structures and the
Okay.
properties of covalent compounds.
Okay.
So what are covalent structures like? Right? The compounds. Yeah, go ahead.
Yes, screen stop sharing for a moment.
Can you see it now?
Yeah.
Okay. So compounds that are formed, that contain covalent bonds can have either simple molecular structures or giant covalent structures.
Okay.
Right, and simple molecular are basically you've got molecules like the ones we saw, right? You saw CH4 or I2 or CH3OH. All of these are simple molecular. Why? Because you've got individual molecules, right? So you've got individual molecules of these compounds, and right, they're only the compounds of simple molecular having simple molecular structures, they are formed from only a few atoms. And right, even though they have strong covalent bonds between the atoms of the within the molecule, have strong covalent bonds between atoms within molecule, but right, they have weak bonds between the molecules themselves. So for example, you've got a molecule of I2. So that's diatomic iodine, and that dash is a covalent bond. And you've got another one over here. Or you could take H2 or O2 or N2 or CH4 or whatever you want. Right? And so
Mm.
the covalent bond itself is strong. But any attraction between the two iodine molecules is weak. Weak intermolecular bond or attraction. Intermolecular meaning between the molecules.
Okay.
Now remember we talked about hydrogen bonding some time back
Yeah.
in passing. Somewhere over here, I guess. Oh, there it is. Right? So we talked about oxygen having a slight negative and hydrogen having a slight positive charge, and right. So
Yeah.
I didn't talk about hydrogen bonding exactly. I talked about water. The water molecule is a covalent molecule, right? So we saw that,
Yeah.
and right. So because of that delta negative and delta positive charge, the water molecule that's delta negative, that's delta positive. I think we looked at hydrogen bonding actually, right? So if I go further back, at some point, right, talking about dissolving. So yeah, somewhere over here, in ionic compounds. Okay, that is it. Anyway, so what happens is, right, the iodine atoms, sorry, the iodine molecules aren't really attracted to each other, but oops, not like that. Right, so just an example that the hydrogen atom in a different water molecule will be attracted to the oxygen atom, right, in a water molecule. So these are two different water molecules. The oxygen of one molecule is attracting the hydrogen of another, and similarly, right, the hydrogen of one is attracting the oxygen because of the difference in the slight polar, the polar charges, the slight charges over here. Okay, and these are called hydrogen bonds.
Okay.
So hydrogen bonds aren't explained yet in your syllabus, right? But these are hydrogen bonds, and these, right, are the strongest right of the weak intermolecular bonding that we can get in simple molecular structures.
What do you mean by this the strongest weak?
Just a minute. So we just talked about simple molecular structures having weak bonds between the molecules, and we gave the example of iodine, right?
Yeah.
Now, there are different types of attractions between the molecules happening. Okay? So,
Yeah.
hydrogen bonding, again, water is covalent, but the attraction between the different water molecules, the hydrogen bonding, because of the slight charges on the hydrogen and oxygen atoms within the molecule, just like have this in mind, right? Iodine, the atoms in the iodine molecule don't have any charge on them. So there isn't really much attracting one molecule to the other. The atoms in the water molecule do have a charge on them, right? And we saw in ionic bonding, well, if there's a charge, there's going to be an attraction, and the attraction is going to be strong. right?
Yeah.
And so when you have a charge, even though it's covalent, the different molecules are attracted to each other, and they are attracted to each other strongly, right? But strongly is, right, in terms of it's one of the strongest attractions as far as simple molecular structures are concerned.
Like among the other weak
And yeah,
covalent
so
structures.
you've got N2 and CH4 and CH3OH, right? So the attraction between two nitrogens or two methane molecules, right, or two alcohol. Well, alcohol actually has a charge over here, right? So that's slightly different, right? So the hydrogen bond, if hydrogen bonding is occurring within different molecules, between different molecules of a simple molecular covalent structure.
Basically, among the weak covalent structures, hydrogen is the strongest.
Don't say covalent charges. It's not a weak covalent charge, right? There's no such thing as a covalent charge.
No, no, a covalent structure, I said.
Ha. So the structure is not weak. The structure is simple molecular. Simple molecular because you've got only a few atoms joining together to form the molecule.
Yeah,
Between two nitrogen molecules, between two methane molecules, right? They aren't really attracted to each other as strongly. Water is an
yeah,
example which is where the molecules are attracted to each other relatively strongly. Okay, so the
yeah,
different types of interactions or the bonds between the molecules of covalent, simple molecular covalent compounds, water has the strongest or one of the strongest interactions. Does that make sense?
okay, yeah,
Hmm?
yeah,
Okay. Then you've got the giant covalent, right? So giant covalent is basically, it contains hundreds of thousands of atoms joined together by covalent bonds. Right? An example of that is carbon, right, forming diamond, or the other example that they've given is silicon, right? Silicon 4 oxide. So, right, if I draw carbon, right, in diamond, each carbon is bonded to four other carbons. Can you see that?
yeah,
And you just, now it looks like a layer, sort of. It's not exactly a layer, but the point is that you can see, right? And so it's not just like a few atoms, like CH4 has 5 atoms and CH3OH has 6 atoms, right? You can see that, it's like it would be a massive structure if you just draw this out, right?
yeah,
So you can look at the book, and they've given you an illustration of what silicon 4 oxide,
okay,
oxide would look like. They've also given the structure of diamond, which is C4, and graphite. Now we will talk about diamond and graphite is C3. Okay,
yeah,
so we'll come to diamond and graphite, but right, so you can take a look at the structures in the book. I have tried to draw something, right, to represent diamond. Okay, Now, what are the properties of covalent compounds? Right, so the simple molecular structures, the simple molecular compounds are usually gases, liquids, or solids, and they have low melting and boiling points.
Mm-hmm.
Right, so low melting points and boiling points. Right, and the reason for that is because the intermolecular forces are weak. So the low melting and boiling points are due to weak intermolecular. Right, now just to further understand what they mean by that, when we talked about ionic bonding, we said ionic compounds have high melting and boiling points, and the reason for that is because the electrostatic attraction between the ions is so strong that you need to input a very large amount of energy. So heat, basically you need to heat them up to a high temperature to actually cause the ions to split, right,
Yeah.
or to move away from each other. And we also talked about the fact that the structure of ionic compounds are lattices, so they form giant lattices, right?
Yeah.
And
Yeah.
so with simple molecular, covalent compounds, you don't have that kind of structure. And because the attraction between the
Molecule.
molecules is right weak, and so right they melt and they boil at relatively lower temperatures. Okay,
Okay. Yeah.
right? If you talk about uh, giant covalent structures, right? So because they have this giant structure where they've got like thousands of atoms bonded by covalent bonds, right? So we're not even talking about intermolecular bonds. The bonds between the thousands of atoms are all covalent bonds, right? And so giant covalent structures have high melting points and boiling points,
Yeah.
right? And they tend to be solids,
Oh, okay.
right? Why? Because, right? Okay. Uh, then they generally do not conduct electricity. Right? Why? Because to conduct electricity, you need to have charges or electrons, right? And
Yes, sir.
you don't have charges, so it's not ionic. You don't have free electrons, and so right, you don't have anything like that to conduct the electricity. Right? So they do not conduct electricity when molten or in solution. Generally, right?
Yeah.
In solution meaning dissolved in water. Now, right, we'll talk about its dissolution because, right, covalent compounds also do not normally dissolve in water to begin with.
Yeah.
Okay, there
Yeah.
there are a few, for example, HCl, which we know is acidic, right? Although we haven't talked about acids and bases, but still, right, we know we've come across this earlier on, right? And so HCl is a covalent compound, right? You've got a single bond between the hydrogen and the chlorine, but this guy can dissolve in water, and when it does dissolve in water, it actually breaks up into ions.
Oh, okay.
Right? And if
Yeah.
it's breaking up into ions, it can conduct electricity.
Yeah.
So there are exceptions.
Yeah.
Okay? Now, we talked about dissolving in water. Well, they do not generally dissolve in water.
Okay.
Right? Even though water itself is a covalent compound. Right? But remember those charges we talked about?
Yeah.
Right? That is the reason why ionic substances dissolve readily in water because of the charges. Some of the covalent compounds that break up into ions dissolve in water. Right?
Yeah.
So you've got HCl as a gas over here, and it's dissolved in water, so these are both aqueous.
Mm.
So what happens with covalent compounds? Well, they dissolve in organic solvents.
Yeah.
Right? So water can dissolve, generate, oh sorry, not generate, oops, I need to erase that.
Yeah.
So so water can dissolve some covalent compounds better than others, right? They generally do not dissolve in water. Right? They do dissolve in what are called organic solvents. Right?
Okay.
What are organic solvents? So they are covalent compounds, right? They are covalent compounds, covalent liquids, right? Composed majorly of carbon and hydrogen. An example of that is methanol or ethanol, right? So C2H5OH, right? This is ethanol. It is an organic solvent. Okay?
Yes, sir.
Are you sure?
Yes, sir.
Okay. Then they talk about the different forms of carbon. So here we're going to talk about graphite and carbon. And I will try to move over this quickly so I can talk about metallic bonding. It is not a complicated topic. I want to get it done today so we can start a new chapter tomorrow.
Okay. So we'll complete this now.
I will try to, yes. Again, there's not a lot to talk about.
Okay.
Right? So carbon obviously we know is a non-metal. It can form 4 covalent bonds, and right, covalent carbon can form right different giant structures, right?
Okay.
On a side, right, the fact that an element can form different structures is right. Those are called allotropes.
Okay.
So carbon itself can, right, so they're called allotropes.
Hmm.
Different structures formed by same atoms. Okay.
Okay.
So what can carbon form, right? The ones we're interested in are graphite. And in graphite, right, carbon forms layers
Okay.
of, C3, which means each carbon forms 3 covalent bonds with other carbons. So this is what it looks like. Right now we know carbon can form 4. Right, so what happens to that one electron that is missing? Well, it's what is called, it's delocalized. Right, so it's sort of moving.
It's located somewhere else.
No, that electron from each atom, keep in mind, right? Each atom
Mm.
is, right, one electron from each carbon atom is sort of moving about freely over here. That is what delocalization is. Right, the electron is moving freely between the atoms.
Okay.
Okay.
Yeah.
And because graphite has free electrons, that means graphite can conduct electricity. Okay.
Yeah.
Are you sure?
Yeah.
Okay. And carbon, I did tell you, sorry, not carbon, diamond. I did tell you about diamond. So because you got this huge giant structure, right? And so
Yeah.
diamond is like super hard. It is the hardest material known to man presently.
Really?
Yeah.
Okay, that's surprising.
So again, we know it's a giant structure, right?
Yeah.
C4, right? And hardest material known. Right, as you can imagine, very high melting and boiling points. Right, it is, yeah, so we talked about the hardness. The arrangement is tetrahedral.
What does that mean?
Means it's something like this. So it sort of like forms a pyramid with the carbon as you can like at the head of the pyramid. Sort of.
Okay.
Right, if you take a look at the book, you get a much better illustration.
Yeah. Okay.
And because there are no free electrons over here, it does not conduct electricity,
Okay.
obviously.
Yeah.
Right, diamond can be made artificially by heating graphite at high pressure to 300 degrees centigrade. Right, graphite can be made artificially in as well. Right, it's given in the book. And right, they both have various uses. Graphite is obviously used in pencil pencils, and sporting equipment, lead is diamond is used in saws and drills, right?
Yes.
Other
Yeah.
than just being used for ornamental purposes, the diamond
Yeah.
rings and necklaces and all that
Yeah. Yeah.
stuff.
Yeah.
Right? So
Yeah.
the minor details you can check out from the book, and I
Okay.
want to wrap up with metallic bonding.
Okay.
That's the last kind of bonding I'm gonna do. There's not really much to talk about over here. Right? So what happens in metals is you've got these hundreds of thousands of atoms. Regularly arranged. The arrangement depends on the type of atom we have, type of metal we have. And so
Yeah.
what we have is you've got all these atoms, and what happens is we know that metals lose electrons, right?
Yeah.
So it could be one, it could be two, it could be three, depending on which metal we're talking about. And so what
Yeah.
happens is, right, you have basically positively charged atoms, right? So you can put like a positive charge throughout. You've got positive metal ions in a sea of delocalized electrons. So what happens is all the valence electrons, all the outermost shell electrons are delocalized, right? So they're moving about freely,
Yeah.
right? So you've got electrons. Let me just draw that with a different color. You've got electrons from all the atoms, and the number of atoms depends on which metal it is, and that's what makes metals very good conductors.
Yeah.
Okay, also because of the regular arrangement, right, metals have the property of being malleable,
Meaning?
meaning that they can be formed into shapes.
Okay.
We know that, right?
Yeah.
And ductile, which means they can
Sorry?
be ductile.
Oh, okay.
They can be pulled into wires. We know that as well,
Yeah.
right? They're also dense, right? Why? Because you've got positive ions closely packed, tightly packed,
Yeah.
and the attraction of the electrons, right? So because of that, they're closely packed, and density is mass per unit volume. So you've got more atoms in less space. That increases the density, right? Because of the same reason, positive ions, negative electrons, right? They have high melting points and high boiling points, right? Because the attraction within the metallic structure is strong,
Yeah.
right? So you can see the same concept repeating.
Yeah.
What else do we have?
Nothing.
Yeah. Yeah, and we're done.
Okay.
All right.
Yeah.
And you can obviously, you can and should and do that. Refer to the book. Right. There might be a few minor details that I did not cover, but they're minor, so that's okay. You'll get them from the book. And as you can see, there wasn't really much to talk about metallic bonding, but it is something you need to know, obviously.
Yeah. Definitely.
Okay, and so that's the end of chapter 3, and so tomorrow we'll pick up with
Chapter
stoichiometry.
4.
Yes.
Okay.
Right, the chapter students dread. Foreshadowing. Right? Foreshadowing.
Yeah.
Okay. So I'll see you tomorrow, inshallah.
Inshallah. Okay then. Allah Hafiz.